good morning, or afternoon, depending on when you're watching this. Today we're going to be looking at gears, pulley drives, and sprockets, and we're going to break this up into two parts. So the first part is going to be the gear part, and then we'll look at pulley drives and sprockets separately, just so that this doesn't get any longer than it needs to. So that's kind of the plan. And so we're going to start with looking at gears and kind of work our way through. And so when we look at gears, pulleys, and sprockets, there's really three things that we're dealing with. We are allowing for change of speed, and that's a really common application. If you've ever looked at a watch or a clock that's a older style where it's got gears in it, that's one of its main functions is they are changing the speed of rotation or the speed of the direction of rotation as you are turning that. And then the other thing we can do is change direction of rotation. And you kind of see that when you are dealing with gears, you'll see that as one gear turns, the gear that's meshed with it is going to turn in the opposite direction. So we'll look at that as well. And then the last thing we're looking at is changing the amount of torque available. And so that's also one of the more common purposes for using a gear or a pulley or a chain system. And you see some examples down here. This is out of some sort of vehicle. I'm not sure which kind of vehicle it is, but we've got a gear system. So we've got this larger gear and it's meshing with this one, it's meshing with this one. We've got a compound gear train over here. You can't really see it very well, but that's what's happening there. But what's happening is we are transmitting power from one gear to another. And so as that happens, two things are going to happen, or actually three. All three of these things are potentially going to be happening. We'll be changing the speed, so like the output gear is going to have a different speed than the input gear. We'll be changing the direction of rotation, so if this one turns clockwise, this one will turn counterclockwise. And we'll also be changing the amount of torque. And so we'll look at all three of those things as we go through. All right. So we want to talk about what a gear train is. And a gear train is basically just any kind of a system where we have two gears meshing together to transfer for motion and torque. So it could be a very common gear system like we see with this little clip art down here where it's a what we call a spur gear. And a spur gear is going to be probably the simplest kind. We see those all the time. That's what we kind of think of when we think of a gear. That's why all the clip art looks like that. But there's also worm gears. There are bevel gears. We have kind of helical gears where the teeth are not vertically or like horizontal or perpendicular depending on which way you look at them. But they actually kind of curve along the edge of the gear itself. Lots of different types, rat gears, things like that. So lots of different gear types are out there. But what makes it a gear train is that we have two or sometimes more than two gears meshed together where the teeth are interlocking and those teeth are causing, as one turns, it causes another one to turn. And so we say the driver gear is the one that's causing the motion. And if we kind of go back to what we talked about with mechanical advantage in simple machines, the driver gear is basically like our effort because it's the one that's causing all of the motion to happen. So the driver gear is basically like your effort, and then the driven gear is your output. So we could say it's like the resistance. It maybe has a little different connotation here, but basically that is what we are causing to move as we push through and drive that gear. So if we only have two gears, then the driver would be the input, the output would be the driven. So when we start talking about how this works, then we look at these two gears here. These are gears that are mating. They're mating gears, means that they are going to mesh together tooth to tooth. And as one turns, and again, this one's turning clockwise, it is going to cause the other one to turn in the opposite direction. That's one of the things that is a characteristic of gears, that they are going to turn in opposite directions as they mesh. That's really the only way that could work. You could also have what's called an idler gear. An idler gear is a gear that is between the input and the output. And the purpose of the idler is really kind of dependent on what the situation, but one thing that we'll always do is going to be a transfer of direction. So let's say this is my input gear, If it's going clockwise, this one's going to go counterclockwise. Then when that idler gear connects up to my output, because it is going counter, this one would have to go clockwise. And so what we get then is my input and my output are going to go the same direction. And that's one of the uses of an idler gear is to maybe coordinate the direction of travel of your input and your output gear. One other thing you might see with an idler gear is that it's just there to provide some distance. So maybe my input and my output need to be separated by a certain length in my mechanism, and I don't want to use really large gears to make my mechanism. So a idler gear, or maybe even more than one idler gear, would be one way to transfer that motion over a greater distance. Now, we will see later on that a lot of times when you have that situation, what we do instead is we'll use a belt or we'll use a chain to transfer force over a distance. But if it's not a great distance, if it's fairly close together, it might be to your advantage to just use gears. And so that'd be a situation where you might have that going on. It also is possible, and in a lot of cases it's likely, that this idler gear is actually attached to something else. And so that idler gear may be doing some other task other than just changing direction. Maybe it's got something attached to one other mechanism, maybe in a clock, and we're looking at how, the hands of the clock are going to be attached to these different gears. Maybe that idler gear is the one that's driving maybe the second hand or the minute hand or something like that. So a lot of different ways that can happen. But the idler gear is going to just kind of be in between our input and our output, our driven and our driver. Okay. One thing that we do want to kind of point out, and not that this is going to be a big issue for us right now, but it is a good information to have, is that our mating gear should always have the same size of teeth, not necessarily diameter, but the teeth themselves. If you look at the shape and the size of these teeth, but from one gear to the other, they need to match. Otherwise, what's going to happen is you're going to get binding. They're not going to mesh correctly if they're different sizes, different spacing. So you want to make sure that they're the same. All the stuff we're dealing with, especially with the VEX, they're going to work. That's how they're designed. They're designed to all have the same diametric pitch, and so they're all going to mesh nicely. The other thing you have to worry about is spacing between the two gears, like how far is it from the center of one gear to the other. Again, with the VEX system, it's all designed to work well. So we won't really run into that problem too much unless we try to do something out unusual. But that's something you do want to consider. If you're just going to buy some gears to do some kind of a project, you want to make sure that you're buying the same type of gear, things that have the same pitch, same size teeth. Otherwise, you're going to have problems. All right, so when we talk about gears, one of the things we talk about is how fast do they move. So, when we did the mechanical advantage, we talked about distance traveled. Here, we're really talking about speed, and there's two different ways we can talk about speed. We can talk about linear speed, which is how much distance per unit time, so how many feet per second or inches per second, something like that, or miles per hour. And that is a very useful measurement, but it's really not what we want to look at when we're talking about rotational motion. So with rotational motion, we are going to be looking at how many revolutions per minute, or you can say rotations per minute, but the actual term is revolutions per minute. That's what RPM stands for. And so when we're looking at these gears right here, what we're going to see is that a characteristic, a feature of gears is that if I have two gears meshed together, that when they spin, the larger gear is going to spin slower. And that is because it takes more teeth. You've got more teeth on this. So every rotation of this larger gear, the smaller one, which has less teeth, is going to rotate more often, more than once. So like if this blue one goes one time around, this smaller red one is going to rotate more than once. So it's going to have a larger, greater rotational speed, more rotations per minute than the larger blue one. And that's going to always be true. If I have two gears that are meshed together, tooth to tooth like that, larger is always going to go slower, smaller is going to go faster. Now, the trade-off for that, and we'll talk about that more here in a minute, is that just like in simple machines, we talked about that there was a trade-off between force and distance. If I gave myself a mechanical advantage greater than one, that meant I was going to be able to put in less effort force, but I had to have a larger effort distance. We have a similar situation here. Um, where we're trading speed, angular speed, so angular velocity, so our RPM, is going to be a trade-off for torque. So if I have something that moves slower, it is going to have greater torque. If it goes faster, it's going to have less torque. So if I'm looking at the two gears here, the blue one is moving slower, but if I were using that to turn something, or is using that to maybe do some kind of work, I'm going to get more output torque from the blue one than I would the red one. The red one is smaller, so it's going to go faster, but it's going to have less torque. And part of that torque is coming from the size, and that's part of the reason why this works. Is that the bigger gear has a larger moment arm. So if we go back to our simple machines and talk about wheel and axle type of calculations, larger gear means it's going to have a larger moment arm, so you're going to get more torque that way. The other thing we talk about, since we are talking about rotational speed, is that if they are on the same shaft, like this yellow and this blue one are, those are going to rotate at the same rotational speed, so the same angular velocity. Now, they're not going to have the same linear velocity. If I measure how fast the edge is moving here versus how fast the edge is moving here, the bigger one's going to have a larger linear speed as far as like how fast is the tooth moving on the edge of that. It's going to be moving faster in a linear velocity. But as far as how many rotations per minute it is traveling in, if they're on the same shaft, they have to be turning at the same speed. They're not going to be able to turn at different speeds because they're only going to turn as fast as that shaft is turning. So on the same axle, same RPM, same angular velocity. If they are meshed together, tooth to tooth, larger ones slower, smaller ones faster. All right, so when we talk about gear ratio, what are we really interested in? Well, we have 4 pieces of information that we want to talk about. One of those is number of teeth, one of those is diameter, one is angular velocity. Now, angular velocity, they have W there as the kind of variable for that, and that is actually not the variable. The variable is actually omega, but it's lowercase. It kind of looks like a W. We'll see it on one of the later slides. I'll actually have the correct um, symbol in there. And it looks a lot like a W, so they kind of use W as a fill-in just so they don't have to type in the fancy character there. But that is our angular velocity. And then the last one is torque, and we kind of run into the same thing here. They're using T for torque because it's easier, but the actual symbol is actually tau. It's lowercase tau, which just kind of looks like a T. I mean, it's basically a T. So that's why they use T as the kind of stand-in for this. So what do we care about this? Well, these are the 4 things that are all related to each other, and we can use information about one of these to help us find out something about the other. So, for example, if we know something about the number of teeth of our gear train, we have these 2 gears that are meshing together, that can help us to figure out something about the angular velocity or about the torque. And so in this particular example, if we count the number of teeth of the blue gear, which they're telling us is our output gear, the number of teeth is 12. The number of teeth of my input gear, which is this red one, which has got the N there for input, is going to be 6. And so we can look at this ratio between these two, and that's really kind of what we're going to be doing. We're going to be doing a lot of ratios. So we're looking at the ratio between the number of teeth, and so we can kind of see that's a 2-to-1 ratio. There's twice as many output teeth as input. If we look at the diameter is the same kind of thing. The diameter's got 4-inch diameter on the bigger one. We got a 2-inch diameter on the smaller one. So it's 4-inch to 2-inch. There's that same ratio, same 2-to-1 ratio. And we'll see that the number of teeth and the diameter are really closely related, because if my teeth are all the same size and shape, the only way I can add more teeth is to make my gear bigger. And so there is a definite direct 1-to-1 ratio or relationship between the number of teeth and the diameter, because if I need more teeth on my gear, I can't add more teeth unless I make the diameter bigger. And if I need less teeth, I can't take teeth away and have it work unless I make that diameter smaller. So they are tied together. There is a very strong relationship between those 2 things. The other 2 are going to be a little less obvious, but they work the same way. And that is what we said earlier. The bigger gear, if we have these 2 meshed together, the bigger gear is going to go slower. And what we find is that the relationship between the 2 is tied to the sizes. And so if the smaller one, if our input is 40 RPM, that's how fast it's turning, this output gear, because it's twice as big, is going to be going half as fast, because for every one rotation of this blue one, this red one has to go 2 rotations. So this one's going to rotate twice as fast, angular velocity wise, RPM wise, as the bigger one. And so that's what we see down here. It's a 2-to-1 ratio. The only thing that's different here is because the smaller one goes faster, we kind of have a backwards relationship. So, it's inverted from the other ones. So on all the other ones, we look at the number of teeth or the diameter. The output is the bigger number in this particular example. The angular velocity is opposite. So in this case, my angular velocity for my input is actually bigger, but that's because smaller ones move faster. And then the last one, which they don't have in the picture here, but they're talking about the torques, what we're going to see is that same relationship exists between torque. Bigger it is, the more torque it's got. So the bigger diameter has a larger torque, and it's in that same ratio. So as we kind of go through here, we notice it's a 2-to-1 ratio for all of these. But the only one that's unusual is the angular velocity, because angular velocity is inverted as far as which one's bigger, but it's still a 2-to-1 ratio. Okay. So that's what we're going to be looking at, and we want to look at is, okay, well, what does that formula look like then? And really what our formulas are just a whole bunch of ratios. And they give you all 4 of them as this kind of weird, big, equal thing. But what they're showing us is that all these things are equivalent. And so what does that mean? That means that I can pick and choose which pieces of this equivalency I want. So if I know something about the number of teeth, but I don't know something about the diameter, then I can use number of teeth to help me figure out what the gear ratio is. And I can use that information to maybe help me figure out maybe what my output speed should be, or my output torque should be, or what input torque do I need to get an output torque that I want. So it's going to be a lot of ratios. We're going to be setting one ratio, one fraction equal to another one. So maybe we'll have the number of teeth set equal to the torques, and we use that to help us calculate what the output torque is or what the input torque is, that sort of thing. Or maybe I'm trying to figure out how many teeth I need so I can get the torque ratio that I want. Whatever it is, we're just picking and choosing out of these sets. So we're saying all these are equal to each other. We can pick and choose as needed to kind of set up whatever relationship we need to solve for a piece that we need, that we don't know. All right, so they're going to kind of run through real quick and say, okay, well, what is the gear ratio here? And this is the same example we were just looking at on the last slide. So nothing new. So we say, okay, well, the number of teeth, we said, okay, well, the output number of teeth on this blue one, that's our output one, was 12. We could count out that there's 12 teeth around there. And the input had 6 teeth, so our ratio, our gear ratio, which is just out over n, number of output teeth versus number of input teeth, is going to be 12 over 6. Well, 12 over 6 is 2 to 1. And if we look at the diameters, we say, okay, well, the output diameter was 4 inches, the input diameter was 2 inches, that's going to give me 4 over 2. 4 inches divided by 2 inches. Units are going to cancel because it's just a ratio, so we get 4 over 2. Well, that's still 2 to 1, same ratio. And that's what we want to see. They should all be the same ratio, which means we already know enough to tell us what the gear ratio is going to be. It's going to be 2 to 1. We just want to kind of verify that all of these things work that way. So when we look at our angular velocity, we say, okay, well, for this one, it was backwards. And so we don't want the output over the input for this one. This is the only one that's that way. That's the one you want to watch out for, because that's the one that's going to mess you up. This is the symbol. We said that the actual symbol is later. This is the omega, and it looks kind of like a W, kind of a fancy cursive EW. It's not. It's omega, but it kind of has a W look to it. So that's why they like to use W as a stand-in for it. But it's the input angular velocity, which was the 40 RPM, divided by our output angular velocity. Again, just because we know the output is going to be slower because it's bigger. And so to keep that ratio, we flip the input and output versus the rest of them. And so we'll get 40 RPM over 20 RPM, and again, units are going to cancel. So we get 40 over 20, which is 2 to 1. And then torques, which again are not on this picture, but they told us last time is 80 and 40. So 80 foot-pounds and 40 foot-pounds. And so again, every one of these cases, the ratio always the same. Ratio is going to be 2 to 1. So that is our gear ratio. And what that's telling us, anytime we get a ratio greater than 1, so we go back to like what we talked about with mechanical advantage, if it's greater than 1, that is telling us some information. In this case, it is telling us that our output is going to have greater torque but less speed. So greater than 1 means we have greater output torque but less output speed. That's always going to be the case. If it were less than 1, and again, it can't be negative, can't be 0, but if it's less than 1, if it's between 0 and 1, then it's going to be the opposite. So if we're going with a gear ratio less than 1, that means we're going to have less output torque but greater output speed. So we're getting more speed out, but we're getting less torque. So you kind of have to know that as you're designing to say, what do I want? Am I trying to design something to have more torque, or am I trying to design it to have more speed? And that's going to kind of determine which way do I want my gear ratio to go. Do I want it to be greater than 1? Do I want it to be less than 1? I don't know if any of you guys ever had one of those little Power Wheels, cars that you could have that you can sit in, like 2 and 3 year olds. They can drive them around. They are a really good example of a situation where something like this is happening, where I have a very large gear ratio because the motors that drive those are very, very small. They have very small motors. They have high RPM, very low torque. So they have very little power, but they spin really fast. And so what happens is they have a gearbox, and that gearbox is going to basically do this. It's going to have a gear ratio that's greater than 1, and it actually is quite a bit greater than 1. Well, I don't know what the exact number is, but it's a very big ratio. And what it's doing is it's taking that small motor that has high RPM and low torque, and it's taking that RPM way, way down, and then increasing the torque quite a bit. So you get the torque up enough to where it can drive those little kids around, but the speed is much slower, and so they're not going to drive as fast, but they can definitely have enough torque to move them. So, all right, so we're talking about gear ratios. This is a simple gear train, and all it means to be a simple gear train is that they are all connected tooth to tooth. So we could have as many gears in here as we want. I could have 100 gears. If they're all connected this way, where they're all on separate axles and they are meshed together tooth to tooth, that is a simple gear train. So simple has nothing to do with how many gears, it's just how they are connected. So if they are only connected tooth to tooth and they are not sharing an axle, they're all on separate axles, it is a simple gear train. And so we're going to look at this simple gear train. We're going from A is our input, it's going to turn B is going to turn C, and C is going to turn D. And we want to kind of figure out what is the gear ratio for this system. And the way we're going to do that is we're going to break it down into smaller pieces. And so we're going to figure out what's the gear ratio between A and B. So that's what they're asking for here. Say, okay, well, if A is my driver, that's my input, B is my output, the gear ratio is the number of teeth of the output, which is B, divided by the number of teeth of my input, which is A. Well, that's going to be 12 over 20. So I get 12 over 20. And they're putting it as 0.6. Now, I prefer maybe to put it as 3 over 5. That's just a preference. It doesn't matter. You can put 0.6 if you want, if you'd rather have a decimal. But that is the gear ratio. So it's like 3/5, it's 0.6 to 1. It is less than 1. So again, we're getting less torque, but greater output speed. So B is going to be going faster than A, but it's not going to have as much torque. Okay. All right, so then we're looking from B and C. So now B is the input because A turned B, so B is now going to turn C. So B will be our input, and C is our output for this little group. And we'll say, okay, well, same thing. It's my output over my input, so it's going to be C over B, so 5 over 12. And so that one we get 0.42 to 1. And so that's smaller, and it's just a smaller ratio. And then we say, okay, well, what about the last one? What's the gear ratio between C and D? Well, C and D, C is going to turn D because we're going A is turning B, B is turning C. So C is my input for this little pair. And so I'm going to have my output is D, my input is C. So I'm going to get output over input, so 20 over 5. And we get a 4 to 1 ratio. Okay, so 4 to 1 ratio there. So that one actually is going the other way. So now we have greater than 1, so now we are going to have greater torque at D than we had at C. C has got a lot less torque, but C is going to be going a lot faster, which makes sense. It's going to have to turn, basically C has to turn 4 times to get D to turn once. So it's going a lot slower, D is. All right, so what is the overall gear ratio then? Well, to find the overall gear ratio, what we're going to do is we're going to multiply these together. And this is where I don't prefer the decimal because they've actually rounded 5/12, so it's not exactly 0.42. It's more than that. So if you want to multiply these together, you probably want to use the actual like decimal or the actual fraction of 5/12 when you do this multiplication. But we're going to multiply all these together. So we're going to take this 12 over 20 times the 5/12 times the 20 over 5 and look at what do we get. So if we multiply those together, what is that gear ratio? Well, it turns out if I multiply these together, I end up with just 1 to 1. So what's happening? Well, so what it turns out, and that's what they're saying here, is that these idler gears really don't affect our gear ratios. So when we're trying to figure out the gear ratio for any simple gear train, again, it doesn't matter how many gears are in it, all we want to look at is the input and the final output. And that is going to determine our gear ratio. And if you start looking at the calculations, that's why I like to kind of put this in as decimals or as a fraction instead of a decimal. What you're going to see is there's a lot of cancellation. So when you do like here, I'd have 12 over 20, and the next one's 5 over 12. Well, the 12s are going to cancel. And so the same thing's going to happen with our 5s. So you're going to get a lot of cancellation as we go through this process. And that's how we end up back with 1 over 1. But what it really comes down to for you guys is anytime we're doing the gear ratio for a simple gear train, we're just going to take the number of teeth of the output over the number of teeth of the input. And we don't really worry about these middle ones. They may be important, they may not be. They're going to be maybe doing some other task. Maybe they're just there to make my gear train longer. We don't know why they're there. One thing they will be doing is they will be changing the direction of rotation. Every time we add another one, it's going to change the direction again, back and forth between clockwise and counterclockwise. But they do not do is they do not affect the gear ratio. They're not changing anything with the gear ratio. All that matters is the output and the input. So if we look at that, D over A, it's going to be 20 over 20, and that's going to be our gear ratio. So the next question says, well, what happens if the last gear is 40? So what if we make this D a 40-tooth gear instead of a 20-tooth gear? How does that change things? Well, that's just going to make this last ratio, instead of being 4 to 1, will now be 8 to 1. So you see that last one's now 8 to 1. And if I multiply those together, instead of being 1 to 1, now it's going to be 2 to 1. But we could just figure that out if we said output over input. If this is 40 and this is 20, we'd get 40 over 20 is 2 to 1. So it's going to be the simpler way to go. Could you do it by multiplying all those together? You can, but we don't have to. All right, so one thing we want to kind of do is compare this back to what we did with mechanical advantage and simple machines. And so when we did the simple machines, we talked about actual mechanical advantage was resistance force over effort force, FR over FE. If we take that formula and we solve it for output force or resistance force, what we find is that all we really need to do to find that resistance force or that output force is take the mechanical advantage times our input. So if we take our mechanical advantage times our input, that is going to tell us our output force. And what we find with our gear ratios and our torque, which is rotational motion, not linear motion, is a very similar setup. So we say our gear ratio, if we go back and look at our formula, is that one of our options is that gear ratio is equal to torque out over torque in. So if we take that equation, multiply both sides by input torque, we get the output torque as just the gear ratio times your input torque. Okay, so those are very, very similar. We're just going to see that there is a correlation, kind of a correspondence between how those formulas work for mechanical advantage and for gear ratios. And they're basically the same thing. Now, again, one of those is rotational motion, one of those is more linear motion most of the time. But the idea is the same, that you can make that calculation the same way. And similarly, when we had a compound simple machine, we had multiple simple machines working together, we said, well, to calculate the overall mechanical advantage of that system, we would go and we'd multiply the mechanical advantage of each part together to get the overall mechanical advantage. The same thing is going to be true for a compound gear train. we are going to find the overall gear ratio by taking and multiplying the gear ratio of each individual piece together to get the overall gear ratio. And so if we kind of look at some of these notes here, again, very, very similar, that they're used the same way. It's just the difference is now we're talking rotational motion, so we're looking at torques instead of forces, but the calculation or the setup is the same. And so to find our total mechanical advantage or to find our total gear ratio, we're just multiplying all of these smaller pieces, so all the smaller simple machines, or in this case, these smaller simple gear trains, together to get the overall gear ratio. Okay. Again, they're not calculating the same thing, which is why we can't put these directly together, but you can kind of cheat a little bit and kind of talk about like what the overall mechanical advantage or overall ratio is for a system. But just keep in mind, they're not the same. Gear ratio and mechanical advantage are not necessarily the exact same things, but they are both ratios. So we can kind of fudge it a little bit and talk about them together. Here's an example of a compound machine. And what we're going to see here is that while they're going to call this wheel and axle, it's a lever. We look at this lever and we're going to apply force to this lever, and our lever arm is 4 inches, the distance from the fulcrum out to where the force is being applied. And that is going to cause this gear to rotate. And that gear is going to cause this gear to rotate. And when that gear rotates, it's going to cause this other lever to move. And so we want to look at is, well, what would that actually do? We built one of these one time, and it's actually kind of interesting. This particular setup would actually cause this to output to move quickly. It's not going to have a lot of torque, but it's going to have a lot of speed. It's going to move fast. And what we find then is that this is really good as kind of like a catapult, or something to throw. Think of it as kind of like a throwing mechanism. If I move this one with a decent amount of torque, even if it doesn't move really fast, this one is going to move much faster. It's going to have a lot less torque, but it's going to move a lot faster. And so when I'm trying to throw something, I kind of want that. I want that speed, that linear velocity. I want it to be moving quickly because I want to throw it. Now, you have to kind of weigh the advantage of, how big a thing am I throwing. But if it's something small, like a ping pong ball or something like that, this would actually throw it pretty well. And so what we want to kind of look at is, what is the overall ratio of this system? Because it's not obvious. We can't just look at it and say, oh, it's going to be greater than 1 or it's less than 1. It's kind of hard to tell. So we want to kind of do a little analysis and figure out what's going on. So we have 3 basic mechanisms. We have the lever here on the input, we have the lever on the output, and then we have this gear ratio between here. And this is not that much different than like a bicycle. If we look at the bicycle now, obviously a bicycle is not all geared together. It's going to have a chain system. But just kind of imagine that the chain is running from here to here. So these two are separated, but the idea is very similar. So you can almost think about it like if I'm pedaling a bike, this is kind of what's going on. And so what's happening is I've got this wheel and axle, which again, I think it's probably easier to refer to it as being a lever that's here. And that one, I'm going to look for the mechanical advantage of that. I'm going to look at the gear train between these 2 gears, and I'm going to look at the mechanical advantage of this output lever, or wheel and axle is what they're calling it, but I'm going to call it a lever. So let's take it one at a time, because again, the idea is that we can break this down and then multiply them together to get the overall system. And so we're going to look at this lever first. Now, we do have to make some assumptions, because that's what we always do. We do know DE. DE is pretty straightforward. We're applying our force here. It's 4 inches from the fulcrum, so that is my DE. And then the DR is the trickier one, because realistically, this is probably going to have a bolt through it somewhere along here where these holes are to attach this arm to the gear so that it will spin. But we don't know where that would be, and we don't have any information about that. So we're going to pretend that it's actually attached right along where the teeth is. So basically at the diameter, the edge. And so that way we can use the radius as our value. So it's not necessarily realistic, but that's what we're going to go with. So our DE is going to be 4. Our DR is going to be the radius of this gear. Okay, and that, again, not realistic, but that's kind of how we're going to go with it. And so our DE, which is 4, divided by our DR is 1.5. And again, we're treating it like a lever, even though it keeps saying wheel and axle. We're going to pretend like it's a lever. It's a second class lever. And so we're going to get a mechanical advantage that's greater than 1. In this case, it's about 2 and 2/3, so 2.6 repeating is that ratio. All right. So that's the first part. So that's the first one. And what it's telling us here is that I am getting a mechanical advantage greater than 1. So that means I am able to put in less effort force. So this is actually helping me out. I can put in less effort force and I'm going to get more resistance, or in this case, more output applied to this gear than I'm putting in. In fact, I'm getting 2 and 2/3 times as much force here at the gear as I am putting in here. Now, the trade-off is I have to move much greater distance compared to how far that is actually going to rotate linear distance-wise, total distance traveled. But that's the first part. So mechanical advantage is greater than 1. If we look at the gear ratio, our output is going to be this bottom one, the blue one, because we are turning this top one with our lever. And so as that causes that to turn, we're causing the bottom one to turn. So that's our output. Our input's the big one on top. And so what we're going to see is our gear ratio is the output over the input. So it's going to be the 24 teeth divided by the 60 tooth. And so we get 24 over 60. And that one's 0.4. So that is less than 1. So that's going to be a situation where we're getting less output torque, but we're getting more output speed. So this bottom one's going to turn faster than this bigger one is, but we're going to have less torque. So we're losing torque, but we're gaining speed. So this one was the opposite. This one of what we just found here. So this one is greater than 1. The gear ratio is less than 1. All right, so we got one more piece, which is this output arm. And we're doing the same thing, DE over DR. DE in this case, since we're having this gear turn the lever, that means my DE is the distance from the center out to where my effort force is. And my effort force is going to be, again, since we don't have better information, we're going to assume it is this radius that we're attached right along the edge of the gear. Probably not realistic, but that's what we're going to go with. And then our DR is the distance from the fulcrum out to the FR force, so our output force. And so we're going to get DE over DR is 0.6 over 4. And again, 0.6 is the radius of this gear. And it's 0.15, so it's quite a bit less than 1. So we're getting very, very much a mechanical advantage less than 1 on this particular piece. So we're putting in a lot of effort force. We're not going to get much output. As far as our output force is going to be a lot smaller. However, we are going to get a lot of output distance. And so this is going to move a lot further than the little bit of rotation this is going to go through. So let's say this goes through like an inch of rotation. This thing's going to go through quite a bit more than that. All right, so all those things together, if we take our two levers and multiply those together, our overall mechanical advantage of our lever systems is going to be the 2.67 times the 0.15. So it's about 0.4. So it's less than 1. So that means our overall system here, we're going to end up having less force applied. So FR is going to be less than FE, but we're going to get a greater distance traveled by FR. So again, that's what we want if we want to throw things. I don't know if that's really what we wanted to do, but that's what's going to happen is we're going to have less force but greater distance. So our output distance will be greater. If we combine that, and they're not going to do this here because technically, again, they're not the same. One is measuring torques, one is measuring forces. But if we kind of cheat a little bit here and say, okay, well, let's multiply that times our gear ratio just to kind of see the overall system here. Our gear ratio is also 0.4. So if I multiply my 0.4 times my 0.4, I'm going to get 0.16. So that means I am getting a lot of output speed compared to my input. So it's going to move a lot faster, but I'm also losing a lot of output force. So it's going to not have very much power, as far as like how much force is being applied, but it's going to be moving fast. So if I put enough force on the input, I can throw things pretty well because it's going to be moving quickly. And that's what we wanted. So we're going to be moving not quite 10 times faster, but almost 10 times faster than what we started from. Okay. So our gear ratio is 0.4. All right, so why do we talk about that? Well, because we really want to talk about this compound gear train. And compound gear train is going to be what you see the most of. And there's a good reason for that. And that is because if I want a large gear ratio with a simple gear train, because I'm only looking at the input and the output, um, I can't get really large gear ratios unless I use really big gears. For example, if I wanted a 10-to-1 ratio with a simple gear train, my output gear has to be 10 times bigger than my input. Well, if my input gear is like 20 tooth gear, that means my output gear has to be like a 200 tooth gear. Well, that's not real practical in a lot of cases because those, 200 tooth gear is pretty big. So it's going to be heavy. It's going to be, a really large diameter compared to everything else. So, it's probably not going to fit into this mechanism that I want very well. And so getting large gear ratios with a simple gear train is problematic because I either have to have a really small input gear, which is not always a good thing, may not be able to have a super small one. I mean, we probably aren't going to get much smaller than maybe 10 to 12. It's a pretty small gear. That just means that my output gear has to be really big if I want to use a simple gear train. So what do I do? Well, we introduced the idea of a compound gear train. And a compound gear train is really just two simple gear trains, or it could be more than two. It could be multiple simple gear trains that are tied together. And we'll look at how they're tied together here in just a second. So what we're going to do is we're going to take our driver gear and we're going to attach to that its driven gear. So this is just a simple gear train. We've got this yellow and the green one meshed together to form a simple gear train. And so to make a compound gear train, what we're going to do is instead of taking our other gear and putting it so that it meshes tooth to tooth, we're going to have it share the axle of our output. So now these two are turning at the same rate, same RPM, rotational motion. And so the blue one is not actually part of that gear train. It's on the same axle, but it's not part of that gear train. That gear train is just the green and the yellow. And the blue one is just hitching a ride for right now. So what we're going to do is we're going to take this red one and we're going to make a simple gear train between the red and the blue. So now the red and the blue form a gear train. The green and the yellow form a gear train. So I have two simple gear trains that are connected together by that shared axle. And by connecting them together by that shared axle, I am able to basically transmit the gear train of the first one into the second one. They're connected together by that shared axle. And so what happens? Well, now the gear train, the overall gear ratio is determined by the two separate gear trains multiplied together. Now we have a compound machine. We have two separate gear trains, and we're just going to multiply them together to get the overall gear ratio of the system. Okay, so anytime we have a compound gear train, this is going to be the common aspect of it, is that your output of one gear train is going to be sharing a shaft or sharing an axle with the input of the next simple gear train. And again, you can have multiple of these. You can have as many as you want. I mean, there are some practical limits about what can work or not work friction-wise, but if you look at a lot of them, like that Fisher Price little Power Wheels cars we talked about, that one's got probably 5 separate gear trains kind of working together. I think it's 5, maybe more. But it's got multiple gear trains working together. So you can get really high ratios, and that's what you want. You want a really high ratio, and especially in an application like that, because those motors turn at several thousand RPM, and they have very, very, very low torque. So the motors are not going to be able to turn the wheels and drive that car as they are. They need to be stepped down quite a bit, and that's what's happening. Is you're taking that very high RPM, low torque motor and turning it into a low RPM, high torque motor by using a gear train, and in this case, a compound gear train. So let's take a look at what that would look like. For this one, you have A and B, which again is our first gear train, and A is the driver, B is the output, A is the input. So we want to look at the gear train here. It is going to be the output, which is 40 teeth, divided by our input, which is 10. And so we're going to get 40 over 10, which is 4-to-1 ratio. And then we take a look at the second one. Well, the second one, our C is the input there because it's being driven by this first gear ratio. This first simple gear train is turning B, which is going to turn that axle, which means C is the driver for this part, and C is going to drive D. D is my final output here. And so it's my output, which is D, over my input, which is C, so 50 over 20. And so my gear ratio for that part is 2.5. So neither one's really huge, 4-to-1 and 2.5-to-1. They're not huge gear ratios. However, because they are connected, we can get the overall gear ratio. Like if I turn A, what is D going to do? Well, that overall gear ratio is going to be the product of those. So we're going to multiply this gear ratio times this gear ratio. So 4 times 2.5 gives me an overall gear ratio of 10-to-1. So now I can get a large gear ratio, a 10-to-1 ratio, but I'm not having to use a 200-tooth gear or something huge. I guess in this case, be a 100-tooth gear. If I had a 10-tooth input, I'd have to have a 100-tooth output. Well, now I can get by with a smaller one because I have used the compound gear train. And so that allows me to use a smaller overall gear size. And that's why this is really common. So you see lots and lots of compound gear trains for that reason, because I can use smaller common size gears and not have to make this really large gear to make this work. Okay, so compound gear trains, you're going to see a lot of them. I'll give you some examples in a later installment of what that would look like. But we're going to end this here, and then next time we will look at pulleys and sprocket systems. So thank you very much. We'll talk to you later.